Glad I'm the first one in the marathon run for 4.5 hours of presentation. So hopefully I don't put you to sleep. All right, so I'm Arijit Sinha, a faculty member in Wood Science and Engineering, College of Forestry here. Today I'm going to talk about the publicly funded research projects through TDI, ARS, as well as through USD and NSF and other granting agencies. So essentially I'm going to talk about three different projects. One is on mass ply panels. The other one is on durability of mass timber connections. And the third one, which is giving Judith some sleepless night because of we are occupying the strong floor, is the innovative lateral systems. And that's going to go up for another few months, Judith. I'm sorry about that, but we'll soon vacate it. And then, all right, thanks. Thanks for the endorsements. So MPP, it's no secret that we had a very good relationship with the Ferris Lumber Company, and we helped optimize a lot of their product design through different grants and so. But for this presentation, I'm going to talk about a project that was in conjunction with TDI, ARS, and Wood-Based Composite Center, which is a NSF Industry University Cooperative Research Center, where we looked at characterizing structural properties, as well as looking at operational, to define the envelope for operational condition within the MPP plant itself, and how moisture and relative humidity on a daily basis changes performance of the panels itself. So first task was, which is a bread and butter of our research group, is to characterize mechanical and structural properties of MPP. So we took all the properties we could think of: bending, tension, compression, post-peak plasticity for a lot of these tests, shear, in-plane shear properties, connection tests, seismic performance, or MPP shear walls. And we ran through a battery of testing and got the results out. All these are publicly available through various journals. If you don't have access to them, just reach out to us, to me or anybody in TDI, and we can get you a copy of those papers. And they're all in the public domain itself. So we did a complete characterization of that. And then for the next part, we installed some sensors within the MPP plant in Lyons, Oregon, at the Ferris Lumber Company's new plant, and tracked relative humidity, temperature, moisture conditions for a year in the plant itself. And also, we did a separate component in the lab where we did a lot of, we harvested a lot of specimens off the line. And then we ran through a battery of testing, small scale testing for durability assessment of the adhesive bond line, which involved automatic boil test on a lap shear specimen after bazillion cycles. Also looking at wood failure assessment, and then also doing some short span shear tests, as well as block shear tests. So all the results are, all these tests are completed, and the year that we chose to log the data was 2020. And we had some interesting results because if you recall 2020 Labor Day, we had a huge fire next to the MPP plant, and that really gave us some interesting data points to look at, which we are still sifting through, and the results are available as Matthias Wen's thesis in the OSU library, but we are working on a publication and a TDI report that'll come out soon. So that's that part. Then we move on to durability of mass timber connections. And over the years, TDI, USDA, and private stakeholders have funded a lot of different durability related projects in mass timber connections, and that durability at elevated temperature or elevated temperature performance, moisture degradation profile, and also biological durability, which is after inoculation of fungi or different types of fungi, brown rot, white rot fungi, how does a connection strength degrades over time to characterize a temporal degradation. Elevated temperature stuff is, again, all published. It's out there. Reach out if you need a copy. This is the team, partners in crime. Fred and Jeff have moved on from OSU. They look a lot younger, and I can take credit that this project really aged them. And then John's recovering from a back surgery, so he couldn't be here. And Andre should be here because he's presenting next. So other than that, we had a lot of, we have a bunch of postdocs, Tuho is in the back of the room, and FRAs working on the project. As you all know, it's designed for dry use. CLT is designed for dry use, or mass timber is designed for dry use, but then life happens during a construction site. PV Hall was built almost in the winter with a lot of rain. There were accidental spills, and once moisture ingresses, there is a chance of biological degradation in there. And here comes Andre. So our research objectives were to look at connection degradation and characterize connection degradation after simulated flood exposure, simulated rain exposure, and then a related biological degradation profile we wanted to establish. And we wanted to expand it to all species of CLT because all these are species related. These are not, so species have an important effect in how a fungi could affect different kind of wood, how moisture interacts with southern yellow pine versus Douglas wood differently. So we took 4 different species, the 4 major species that CLT is manufactured of: Douglas fir, Norway spruce, SPF, and southern yellow pine. Did a floor to wall connection using this brackets, which are now in SPIDWIZ. At the start of the project, they were not in SPIDWIZ. These are the brackets that was developed out of the FEMA P695 project, and ran them through. So these are the details of the bracket. Ran them through a series of cyclic tests, but after exposure, after submerging in water for a variety of different timestamps, and then harvesting them, drying them, and testing for a strength and stiffness degradation. And then we have what we call the MECMEC, which is modular, multi-climatic modular environmental chamber. And we use that to simulate some rain exposure over a period of a few weeks, and how rain would affect, the idea was how rain would affect the connection strength and stiffness. We did that. We ran tests for about 120 specimen on this phase, about 120 on the other one, and then analyzed the data, published the results. Again, they're available. They were published last year and this year, available publicly in there. For this phase of the project, I'll talk about a little bit about the biological degradation. And instead of giving you numbers, this is what it looks like after inoculation of fungi after 14 months of, if you keep the fungi there for 14 months, where the connection is totally covered with the fungi itself. And this is Postea placenta, which is a common brown rot fungi available freely anywhere essentially across the US. It might be hiding in this building too. And then if you look at the strength and stiffness over a period of time, the experiments are still going on. We harvested the results show after 40 weeks of exposure. Our last set comes out after 1.5 years of exposure, which we are yet to test. And then you can see there are some degradation. There was a very marked decrease in energy dissipation characteristic of the connection itself, but there is a strength and stiffness degradation as well over the 40 weeks. So again, the conclusions were fungal decay in wood. It degrades property. There is, and it's a species dependent phenomena. And we are trying to discern more nuances within the data we found and also adding to the time period. With that, I move to the LE project, which is the Emerson Lab Launch Initiative. So when we designed the lab, we said we wanted to test a 3-story building in there, and we did, and we had this project to do that.
Maybe you could talk to this one.
Sure.
It's got to turn on there.
All right, so when we designed the lab, we wanted to test a 3-story building in there, and this project does exactly that, along with giving Judith some headaches about the lab space. But again, partners in crime, Andre and Barb Simpson, who has since moved on to Stanford. We won't hold that against her. And Gustavo, Fernando, and Tuho are the PhD students and postdoc respectively. So the idea was to come up with laterals, innovative lateral solutions for more resilient structures. So to reduce the downtime of, to increase the functionality, reduce the downtime after a seismic event, And for that, we kind of created two different innovative lateral systems, and we tried to investigate its performance at a full-scale structural level using a 3-story building as a testing vehicle. So this is what it looks like. It's a 40 by 40 foot plan, 3-story tall. The story heights are between 9 and 10 feet each, and it doesn't use a single piece of CLT. It's all veneer-based products, LVL beams and columns, mass ply panels as your diaphragms, and then mass ply panels as your shear walls. The idea is to go quasi-static cyclics very slowly to simulate kind of the back and forth movement. The loading direction, as you see, is using 3 actuators synced together with the reaction wall, and we go back and forth in that direction. And we will test 2 different lateral systems, one after the other. So we'll test one, and then we'll detach that and attach the other one, which is the UFP solutions, and test that. And then we are in talks with a couple of other folks where we could add a 3rd phase where we bring in another lateral system and test that as well. So the first lateral system uses BRBs as it's a pivoting mass timber wall with buckling restraint brace frames as one of the energy dissipators. And that's how it looks like once it's constructed. You have a shear key, you have BRBs, which is connected to the wall itself and into the foundation. The second one is a standard UFP solution, but with mass plywood panels, and all the UFPs are concentrated at the bottom rather than distributed along the height of the floor. And this is, many of you in the room are familiar with this kind of connection from for the wall to the diaphragm, especially Eric here with his experience at the Nihiri shake table test in 2017. So it's a similar solution that we have where we are transferring force from the walls to the diaphragm, or from the diaphragm to the walls and down to the foundation. So some pictures from construction. All the panels were, all the material was donated by, the LVL was donated by Boise Cascade, MPP was from Ferris, Simpson Strong Tie was generous enough to donate all the connections. We fabricated all the specialty connections that we needed. All the panels were CNC'd out here in the Emerson lab, where we have a CNC, and thanks to the awesome TDI staff to get it all ready and squared up. Then Fortis came in and constructed the specimen for us, and it took them about 3.5 weeks to put everything together, and they were out of the site in 3.5 weeks. So we had some out of plane walls to give us some torsional stability, and those were also MPP. That's what's going up. Then the floors coming in, flying in as well. A lot of screws, diagonal screws going in. So it was fun to watch. Grad students were happy they didn't have to do it. That's the UFP wall that's going up. Again, more BRB. This was new for all of us, and it was really fun process to have it constructed and erected itself. And then once the first story got up, it was really quick. After that, the 2 walls were vertical, all the slabs were in place, and then we could just build floor by floor, and that's the construction completed. So we did do a push on the gravity system itself to get some baseline stiffness data. And our first push of the BRB walls, or the first test, is scheduled for November 15th. So this is, take it as part of the official announcement that we are inviting you all to witness the test, if you will. And Evan will follow up with an official TDI invitation with an RSVP. But if you want to show up, please do, November 15th. Second test, which is the UFP system, would be about 4 weeks after that. Again, an email will follow and give you a detailed timeline of that. And this cannot be done alone. So apart from us, the PIs, the students, there's a lot of people to thank, especially all our material donors, Ferris, Boise Cascade, Simpson Strong Tie, Fortis, Carpenters Union helped out. Eric here at Holmes helped out with design, as well as KPFF, Woodworks, Scott Brenneman was of great help. ARS, who funded it, along with Tollywood Design Institute. And also we could leverage some funding out of NSF for the 6-story using some of the stuff we did for the 3-story building. Talking about the 6-story, I will leave this up here because Andre might have some things to say how is all connected together, how the 2-story, 3-story, 10 and 6-story is all connected.